Hello engineers. May audible? I hope may audible. Yes, please, everywhere. Okay, so last class we discussed about that common source amplifier. So let's revise it. Okay, so what we discussed till now. So starting from the common source amplifier. So let's start with that. Okay, so that common source amplifier means what? We are providing the input at the gate and we are taking the output at the drain, and the common part is source. That's why it is a common source amplifier. And I am saying that okay, this is input and you are taking the output at the drain, and this is your ground. Okay, and this is your resistance. Okay, and of course the body is connected to source. As you know that VSB is 0, so VTH will be VTH naught. The threshold voltage will not affected with the source to body voltage. If VS and VB have a different potential, so VTH will be increases or decreases as per that effect of VSB. Okay. So whenever you are setting that common source amplifier or any type of amplifier, you fix that operating point. That first region that you start with this, ki, okay, you set the biasing in such a way that you set the operating point. Okay, it is just like this, ki, okay, whenever you have a track, okay, this is a track, it is like this, okay, and if you are looking from the outward side, it is a non-linear. But if you set the operating point, let you are setting this is a operating point. At this point, if we are talking about some changes, it is looking like a linear. Okay, you can understand in such a way, or you can think like this, okay, you have a ID versus VGS graph. You have a VGS, you have a ID. The drain current, it depends on the VGS, and this current is like this. Okay, ID versus VGS, and I am saying that okay, I am fixing, let this is a, okay, let this is the point where this is a operating point of the gate voltage, that is Vx, and at this point you have a some Ix. So this is the DC voltage. At the DC voltage you have a DC current, and you changes something, let you have changes some Vx, let is delta Vx. On the basis of that you have a current like this. Okay, and the current is fluctuate like this. So a small amount of change of the voltage, you are finding the large amount of change in the current. Similarly, if you are talking about the V out, so what is V out? V out basically what? That V out is equal to VDD minus IDRD. Yes, this is the voltage V out, that VDD minus IDRD. The current is changing as per the gate to source voltage. Similarly, V out is also changing as per the current is changing, because V out is equal to VDD minus IDRD. Let RD is fixed here. So VDD is fixed, RD is fixed, the current is changing. Your V out is degrading with the ID is increases. When ID is 0, V out is VDD till V out till that ID is 0. Before that VTH, let this is a VTH voltage of the MOSFET. So the current is 0, V out is VDD, and as per that current is increases, this is decreasing like this, and this will be a point where that it will be a linear. Yes, I am just saying that this is V1. Okay. So what is happening at the output side? if you are taking that this is Vx, so I am taking that this is Vx, okay, this is the point at Vx, this is the point at here, and this is the point at here. Okay, so this is the output voltage. So the output voltage like this. So for a small change of the input voltage, you are finding a change on the output side. That is called delta V out upon delta V in. That is called gain. So whenever you are talking about that amplifier, any type of amplifier, you set the operating point firstly. You set the operating point, and after the operating point you will go for that a small signal model, where you are designing a model in such a way that all constant voltage or current will be zero. So VDD is zero, your current will be open, because current is zero means it is act like an open circuit. So those are not changing, it will be a zero, because this is a small signal model, is also called a change model. The model where that you have a change something and you find the change on the output side, on the change of the current. Rest, those are fixed value whose will be zero. Okay. So those are fixed voltage or sources. So it will be zero. Remaining you have a conversion from MOSFET to a small signal model. Okay. And then you determine that gain, impedance, input impedance, output impedance, like this. Yes. So one of the circuit is where that common source amplifier with a resistive load. You have a resistance as a load, and in this circuit you have a gain is what? You have a input voltage, you have a resistance, you have a this, and once you set the operating point, for a small signal model it will be act like a short circuit, it will be act like a ground, and this is a resistance and this MOSFET, and here it is not a DC voltage, it have a some delta Vx, that is a small change in voltage, and you talk about delta V out. And after that you talk about the small signal model. The small signal model is like this, okay, you have a voltage, you have a like this, this is R0, this is GM VGS, and that gate voltage is Vx, and you have a RD, that is a rain resistance, this is grounded, and source is also grounded. You are talking about V out. Okay. So what is V out? V out is basically GM VGS with the parallel of R0 parallel of RD. So that current is multiplied with the resistance, it will have voltage. So V out will be what? That is GM VGS. VGS means what? Vx minus 0, that is GM Vx R0 parallel of RD, and here that current is entering to this side from ground to upward. So that's why it is a negative. So this is minus of GM Vx R0 parallel of RD. And if you talk about gain, that is V out by Vx or V out by V input, it is minus GM R0 parallel of RD. This is the gain there. Okay. So common source amplifier with a resistance load, the gain is minus GM R0 parallel of RD, and you can focus it that RD can be a diode, can be a current source load, because RD is a problem for a fabrication, that resistance value will be high for finding that higher gain. So if you are using a 10K and or 5K or 9K or 11K, it will be a problem, okay, to fabricate in a layout. So we can use a MOSFET, okay, in place of RD. So you mostly think about this equation, that is minus Gm R naught parallel of Rd, and we change that Rd with respect of MOSFET, with respect of current source, load, or anything. Okay, so this is the way you can. Okay, and if you talk about input impedance and output impedance, what is the input impedance and output impedance? That MOSFET, and you are looking at here, what is the input impedance? The gate is not connected to drain or sets, the gate is open. Why? Because this is metals oxide semiconductor. This is oxide. That the here, if you have an input, you have an input at here, the current is zero there. So Z input is what? That current is zero and voltage is Vx. So basically the input impedance is infinite there. And if you talk about output impedance, what is the output impedance? So whenever you are talking about the Z out, you must make it Vx is 0. If Vx is 0, it will be act like an open circuit and R not parallel of Rd. So Z out is, the output impedance is R not parallel of Rd. Yes. Or if you are interested to directly find out, that you can simply say that this, the impedance, it is a R naught. Here you have a Rd, the output impedance at here, the Z out is equal to R naught parallel of Rd. Yes. Okay. In the next, we discuss that you have a MOSFET here. Now I am using a MOSFET. Let I am using a PMOS, and I am using as a diode here. In the place of Rd, I am using a diode, and this diode have a, I am using that like this. Okay, the load is diode connected. This is a diode connected, and this is that value. Let I am saying that this is M1 and this is M2. What will happen? So whenever you have a diode connected, I know this is the simple MOSFET, but now I am changing this Rd with a diode connected, that is PMOS. Okay, so if I am interested in what is the value of this in terms of R, so I can just use it as a diode, and I am using here that one voltage here, that is Vx, and I am finding it Ix. It is just like this, okay, you have a one impedance, that is Z, and I want that value. I am putting that one voltage across it and find that current. V upon I will be your Z value. Similarly, here I want that what is the resistance here in a small signal model. So I am just using Vx and flow the current Ix. What is the current? That will be your R value. Okay. For a small, this will be a grounded, and you can use simply what, that is a simple model here. This is, I am saying that this is R naught 2 because this is M2. So I am lighting this, is it? And this is GM2, VGS2. Okay. And this is that you have a Vx here, and of course this Vx is here. Okay. And you find that Ix. Okay. Yes, is it? So that you will calculate it, what will be that value? That Vx upon Ix will be your 1 by Gm plus, or I can say that approximately this is 1 by Gm. Yeah, 1 by Gm2. Okay. So you calculated that the value is 1 by Gm2. Okay. So that is 1 by Gm2. Okay. Parallel of R02 is also coming, but I am not taking that parallel of R02. So this is nearly about 1 by Gm2. Okay. So I can say that in the place of this MOSFET, I can like write this R value is approximately 1 by GM2. Okay, in a small signal model. It is like this. Yes. Is it okay? And you will set that okay, whenever you have an input voltage, you have a gain. What will be the gain when you have a resistance? The resistance and you have a gain is what, that is V out upon V in, is in a previous case that is minus GM, that M1, that is minus GM1 R naught 1 parallel of RD. Now RD is changing. Now RD is become 1 by GM2. So this is minus GM1 1 upon R, that is R naught 1 parallel of 1 by GM2. Okay. And this become minus GM1 upon GM2. Yes. The gain with that common source amplifier with a diode based load. If you have a diode as a load, now the gain is minus GM1 upon GM2. So what is the problem and what is the benefit of that? The benefit is this, okay, you have a GM1 and GM2, so you can write as minus, that is formula, that is 2 and 2 mu n COX W by L of 1 ID1 upon under root 2 mu n COX W by L of 2 into ID2. This is the formula of transconductance, GM formula. Okay. So both are in series. So ID1, ID2 will be same. That mobility will be same. Everything is same. It is just like that formula have only that W by L of 1 upon under root W by L of 2. So you can increase the gain with the respect of only W by L. If you increase the W by L of 1, the gain will increases. But the problem is, if you are increasing the width of the MOSFET, what will be happen? The parasitic capacitance will introduce. As per the width will increases, as per the parasitic capacitance will increase. C is equal to epsilon A by D. So the better thing is this, ki if you are using a diode connected base circuit as a load, so there is no any value of mu and COX and something like that value parameter variation, but that effect of W by L of 1 upon W by L of 2 under root. So you can increase the gain with respect of W by L ratio. But if you are increasing the gain for increasing the W by L, it will be directly affected your parasitic capacitance. That unwanted capacitance will increase. Okay. So that will be a problem. Okay. The second one is the problem is swing limit. If I am talking about this MOSFET, that is PMOS as a load, and here you have a NMOS, you have a V in and you have a V out there, you have a VDD. So now what is happening? If I am looking this circuit, so what is VSG? This is V out there. So VSG greater than mod VTH. This is the condition for MOSFET will be on this MOSFET, that M2. So what is source voltage? The source voltage is VDD. The gate voltage is V out greater than mod VTH. So V out is less than equal to VDD minus VTH, mod VTH. So I can say that V out never be reaches to VDD. In a previous case, whenever you have a resistance, the MOSFET swinging from the VDD to something value that VD side to make that MOSFET in saturation region. But now the swing limit is limited. So V out is not swinging from VDD to VD side. It is swinging from VDD minus VTH to VD side. So it is like this, okay, the output in a previous case it is swinging from VDD to some value, we decide for a saturation region, now it is swinging from VDD minus mod VTH there. It have a difference of mod VTH. The swing limit is not to VDD, it is less than one threshold voltage. So this is the happening like this. Yes. Is it okay? So of course the gain will be decreased. The gain is not that much. Gain is low in the common source amplifier with a diode connected load there. Okay. So that is one of the case. Let's talk about if I am using that one MOSFET that is act like a current source load. That is active load. Okay, I am using V input here, and I am using one MOSFET here, that is V bias here. This is VDD, and this is V out. Okay, or make it like PMOS. Okay, if you are using this one now, so take as PMOS as a load. So PMOS as a current source load. I am using a current source load that is not a diode. I am using it is act like a current source loads with the MOSFET. Yes, it is similar like this there. It is act like this. So now I am using a MOSFET, that is a PMOS, as a current source load. So what will happen? So I generally use that. Firstly I figure out what is that R. Let this is M1 and this is M2. So what is the value of R here? I am just taking that small signal model. So this is grounded. This is connected like this. This is V bias. This is a DC voltage there. The DC voltage in a small signal model become a grounded. So this is also grounded. This is also grounded. And I am saying that this is Vx. And you are talking about what is Ix. Okay. So if you make a small signal model of this circuit, so this is like this. So here you have a Vx and you have a Ix. The gate voltage is 0. The drain the source voltage is 0. Make it source is like this. Make it source is grounded and make it drain here. Okay. So basically what is happening, the gate and source is 0. So this is not present. GM-VGS is 0. That is VGS is 0. There is not present. So there is only a one resistance that is R02. So whenever you have a gate and source are biased, whenever gate and source are biased in a PMOS, that R will be R02 there. For M2 it is R02, this is R02 only. So I can say that the circuit will be like this. Yes. Okay. In the place of R, it become R02. And now the gain will be what? The gain will be minus GM1 R01 parallel of RD. Now RD become R02 there. So this is minus GM1 R01 parallel of R02. Okay. So of course that R01 R02 will provide a higher resistance, and by the higher resistance with the multiplication of transconductance will provide the high gain. So now this will provide a higher gain as compared to previous one. In a previous one, minus GM up GM1 upon GM2, and in a resistance minus GM1 RD parallel of R0. So if RD is higher, so it will be problem for a what? It will be a problem for making that MOSFET in a linear, maybe enter in a linear region, because V out is equal to VDD minus ID RD. Okay, so I can use this circuit also, and the V bias and VDD becomes 0 in a small signal model, because that gate and source is 0, so VGS will be 0. Here is only a resistance, that is R02. Okay, this is minus GM1 R01 parallel of R02. Okay, and that R01 and R02 is very heavy value, so the gain will be higher. Okay, so this is the way you can. Okay. Let's talk about source degeneration. Till now, we uses a resist, we make it R, that source is always ground. Now I am using a circuit like this. Okay, you have a resistance, you have a like this, and now that source voltage is not 0. Till now, in a previous case, all the cases the source voltage is grounded. Now I am using one resistance here, that the value is RS, and this is RD. You can use RD, you can use diode connected, you can use a current source load, you can use anything. Okay, that the name is RD. If you are using a diode connector, it will be 1 by GM2. If it is current source load, that is R02. Okay, it's up to you only. So that's why I am giving that concept. I am not giving that key you can use anything. Okay, just think in such a way ki, okay, the value of RD is what? That is 1 by GM2 or R02 or RD. Okay, so that always remember that the gain of the common source amplifier is minus GM-RD parallel of R0. What is the RD value? You will find it with a different case. Okay. So this is VDD, you have an input and you are talking about the output here. And this is called source degeneration. This source voltage is not grounded. It is not source voltage is 0. Here the source voltage is connected with the RS. So what is the use of this RS? Just figure out what is the use of this RS. So whenever you have a providing the input voltage, the input voltage will be increased. Let's just think in such a way that input voltage increases, the drain current will be same here also, because they are in series. So if the input voltage will increase, the drain current will increase. Okay, this voltage at Vs is equal to ID into Rs. It is also increased. And that VGS is what? That is, what is VGS? So VGS is equal to V in minus ID into Rs there. Till now VGS is only V in. In a previous case the source voltage is 0. So VGS is only V in. As per the V in is changes, as per that your output, your current is changing. Now I am using one resistance that is called as negative feedback. You can think in such a way कि okay, you have a motorcycle and there is no any speed limiter, there is no any speed limit. You can accelerate and it will speed up. Now I am using a speedometer. The speedometer will show that ki speed limit. Okay, as per you accelerate, it will speed up. But this resistance will also provide the feedback to your brain ki okay, that the speed will increases, that may be a problem of accident. So the negative feedback, what will happen? If this voltage will increase, the current will increase, this voltage Vs will increase, the VGS will decrease, the current will also decrease. Till now VGS is only a V input. Just compare both circuit there. Let you have an input. VGS is what here? That VGS is V in. As per that VGS is changing, there is no any feedback. The current is increases with that ID is equal to 1 upon 2 mu and CUXW by L VGS minus VTH ka whole square, and that will be a ID. VGS is V in. But now you are using VGS in such a way that RS is present. So this is act like a feedback. This is a negative feedback. As per that you are increasing the input voltage, this voltage will also increase. Total VGS will be V in minus ID into RS. Just think in such a way कि okay, you have a operating point. Let you have set the operating point is Vx, and any noise is coming here. Let any noise is coming here. On the basis of that, it will be amplify the noise. Hello? Is it? Now you are setting that operating point. Now you have a noise here. It will be, the current will be increases in also here, and the VGS will be compensate this voltage, compensate this current voltage, and make it that a same current. It is trying to behave like a negative feedback there. That's why it is called source degeneration. This is useful in a differential amplifier also. Whenever you require a RS, that whenever you require a negative feedback, you can use this RS. This RS will help you that this input will not directly affect your circuit. Okay. Okay, you have a bike, and in your bike you have a speedometer that you accelerate it, that every time that speeder show you okay what speed you are gaining by the acceleration. Okay, and your brain is behave like a RS. It is indicating you okay your speed is too much high, please down it. Here that RS it behave like same thing. You have an increase in the input. This RS, that is Vs into Vs is equal to ID into RS. This source voltage will be increases that compensate that voltage, that VGS, that V in minus ID into RS, and similarly VGS will decrease, and so then again current will decrease. Okay. So it is not like this that you have a negative feedback. Like in a control system we talk about that you have a GS and you have a HS and like this. It is act like this. In a control system we are looking at GS, HS, and we have a negative feedback system. Here that the containing in such a way that everything is connected to one by one. If you increase this, the current will increase, the current will increase, this voltage will increase, this voltage will increase, the VGS will decrease, the ID will again decrease. Yes or no? Yes. Is that okay? So you can understand the problem is here. Okay, if you have an input and the source is grounded, as per the input voltage increase, as per that V out is VDD minus ID RD. There is no any feedback. Here you have a feedback. Yes, is it okay? So that's why source degeneration is mostly useful in a differential amplifier. Once you design a differential amplifier, you use this resistance RS. Okay. And this will also help you to increase that output impedance. Okay. So we will check it, everything. Okay. So this is the circuit. You have a RS, you have a RD, you have a input voltage, you have a VDD, and you have a V out. Okay. Let's talk about the small signal model. So if I am setting that okay, you have an operating point, on that operating point the MOSFET in saturation region, and now I am making that a small signal model. So a small signal model is like this. and that is GM-VGS. This is the gate voltage, this is the drain, and this is the source. Now I am changing that, okay, what is connected? That source have a resistance RS, so I am connecting RS here. That drain is connected with the RD, so this is connected with the RD. And RD is connected with VDD, and VDD become ground. So this is, and this voltage I am saying that this is VS. Okay, this is VS basically. So what is GM-VGS? So GM-VGS means let that gate voltage V input, not a gate voltage. I am saying that let this is input voltage, that is VG is V in. So GM-VGS is equal to GM-V in minus VS. Okay. So let's talk about it. What is happening here? At this node, this current is entering, this current is entering, and this current is leaving. Okay. So what is the current? That the entering current is equal to GM V in minus VS, that is VS, is it? I am not using as a body here because that body is also present. If body is grounded, so there is some body transconductance also, that is GMB VSB. Okay. So I am just assuming that it is locally connected, that source is connected to body. So I am not taking as VSB. Okay. Otherwise there is one more effect, that is GMB, body transconductance with the VSB. Okay. So GMV in minus VS, and this VD is behave like a V out. So basically I can make it, this is V out here, there. And this is also entering, that is V out minus Vs upon R naught. This current is entering, this current is entering, and this current is leaving. This is like this, this is A, this is B, and this is C. The entering current is equal to leaving current. The entering current is A plus B is equal to C. Okay. So what is that C? That C is what? That simply C is Vs upon Rs. Yes, is it? Okay. Just solve it. What is happening here? That is GM in terms of one line, that you can take it Vs in a one line, or that is GM V in plus 1 V out by R naught is equal to GM plus 1 by R naught plus 1 by Rs is equal to Vs. Okay. This is the equation. I am just taking that Vs on the right side, and the GM V in and V out by R naught minus GM Vs will be this side, and minus Vs upon R naught will be this side. And what is Vs? Basically this current is, let this is X. So this is also X there. Yes or no? So the X current is entering will be same to here. What is X? Basically X is 0 minus V out upon RD. Yes or no? Yes, everyone. That I can say that what is the current X? That is X is 0 minus V out upon RD. That will be same as X into Rs. So the current will be what? That is X is equal to 0 minus V out upon RD. And if I am talking about Vs, Vs is equal to what? That is X into Rs, that is minus V out upon RD into RS. Yes, everyone. Just focus it here. What is happening? This is not any trick here that I am starting from this point. Okay, this is the point where the current is entering. This current is entering. This current is entering. So this is Gm Vgs. This is V out minus 0 upon R naught is equal to entering current is equal to leaving is equal to Vs minus 0 upon Rs. I am using this. Okay, you have a V in, you have V out term, you have Vs. So just Vs converted in terms of V in or Vs is converted in terms of V out. You must Vs converted in terms of V in or V out only. Then only the relation is V out versus V in. Okay. So how can I convert it? I am saying that okay, this is the current. That current will be same for this. That current, that A plus B will be C, and that let this is X. So this is X into RS. That will be a voltage across Vs. What is X? That is 0 minus V out upon RD. So 0 minus V out upon RD. So Vs is equal to X RS. If V out X is equal to minus V out upon RD. So this is minus RD by R minus RS by RD into V out. Yes, hello. Is it okay? So just put it here, minus RS upon RD into V out in terms of Vs, you can. So that is Gm V in plus V out upon R naught is equal to Gm 1 upon R naught plus 1 upon Rs into minus Rs upon Rd into V out. Yes, okay. You can take one side is GMV in and the other side is what? That is this term. So this will be GMV in plus V out upon R naught is equal to what? That is GM plus 1 upon R naught plus 1 upon RS. So GM plus 1 upon R naught plus 1 upon RS into minus RS upon RD into V out. Okay. You can, that is GMV in equal to what is happening here, that is what, that is minus GM RS minus RS R naught minus 1 into V out minus V out upon R naught, and I am multiplying with RD to everyone. So this is multiplying with RD here also. RD here also. Okay. So GM, if you multiply with what, that is okay, why this is RS upon R naught. This is not like this. RS upon R naught. Okay. Okay. So this is okay. That is, you multiply with R naught here. So this is GM R naught RD V in, that is minus GM R naught RS minus RS minus R naught minus RD, like this, into V out. Okay. So what is V out by V in? That is GM R naught RD and this is minus term upon R naught plus RS plus RD plus GM R naught RS. Yes, hello. Is it like this? Okay. So you can say that that is minus GM R naught RD upon 1 upon R naught plus RS plus RD upon GM R naught RS. Okay. And if RS is 0, if RS is 0, let RS is 0, if RS is not present, if RS is 0, if RS is 0, so what is the gain? That gain will be minus GM R naught RD upon R naught plus RD. This is minus GM R naught parallel of RD or not? This is minus GM R naught parallel of RD is R naught RD upon R naught plus RD. Okay, so this is that if RS is present, this will be a gain. If RS is not present, that will be a gain. So of course, if RS is present, the gain is decreasing. Okay, so that RS is useful for set the operating point, because this is not depend whenever you are setting the operating point, that the operating point is not depend only the input. It depends on VGS, where that source is some voltage, that is RS into IS, RD. So that VGS will be V in minus VS. So it is more controllable as compared to previous one when the source voltage is 0. But if you design this for a gain, if your analysis for a small signal model, that RS will be in a bottom side, in a denominator, that will be decrease your gain. So we can use this source degeneration circuit in such a way, okay, whenever you talk about operating point, if you want to set the operating point, you can use as a circuit. But if you design for an amplification, you can change this circuit in such a way. Yes. Hello. So what can we do here? For setting the operating point, I am including the resistance. Once you talk about the small signal model, this RS will be a short circuit. So in the place of RS become a 0, when you talk about the small signal, means you have some signal, means frequency. So I can use a one bypass capacitance here. The bypass capacitance in such a way that the frequency, when the input is a small signal model, at that frequency this capacitance is act like a short circuit. So the gain will be minus GMR naught parallel of RD only. But when you have a operating point, when you set the DC operating point, this capacitor is act like an open circuit, and this RS is present in your set. It will be help to set your operating point. So this is the way we can understand and we can analyze how can we figure out okay, if you have a capacitance, for that value of signal, this capacitance is act like a bypass capacitance, and this is the value. Okay. And if you talk about the large signal, this RS is present. When we talk about the differential amplifier, in a differential amplifier we use a two MOSFET in such a way we have a resistance in between this. I am just trying to explain you what we did in a differential amplifier. This R will help you set the operating point, because this is the VGS. This is the VGS there. But when you talk about the small signal model, this R will be act like a short circuit. Why? Because I am using in such a way, okay, if you have a differential input, let this the way like this, okay, you have a symmetricity and you have a resistance here. This is plus delta V and this is minus delta V. So what is that voltage here? That is Vx. You find it that Vx will be sum of that. If you are using a superposition for delta V, it will be some value of, let both are resistance and you find it, okay. So some value. If you have minus delta V, it will be symmetric on the right side, from the right side. So the from plus delta V, it have a some value. Let this Vx is equal to plus x. For minus delta V, it is minus x. So Vx becomes 0. It is act like a short circuit. Okay. So we will use this concept. Here I can use a one bypass capacitance, because with the bypass capacitor I can say that at that frequency this capacitance is act like a short circuit. In a DC bias this capacitance is act like an open circuit. Okay. Let's talk about what is the input impedance and output impedance. So the input impedance, whenever you are giving the input at the gate, this is metal oxide semiconductor, the input impedance is always be infinite. Let's talk about the output impedance. So output impedance is what that this is and this is. So this is that Z and this is parallel of RD. I am talking about this Z here. So I am designing a small signal model here, that is GM VGS, and this is R0, and here this is V here, and this is the resistance, that is R. Okay, and I am saying that, okay, I am using one voltage here. Let I am using one voltage, that is name is small Vx and high Ix. But by this we can determine what is Vx upon Ix. So I am using one Vx here and this is Ix. By the Vx and Ix I can define it what is the resistance. This is Rs. And the gate voltage is 0 for that, finding the Z out. So what is happening, that is GM VGS is what, that is, you can say that the GM VGS is basically GM gate voltage is 0 and the source voltage is Vs, that is minus Vs, that this is Vs. Okay. And what is Vs? Vs is basically this current is Ix and Ix is entering here, so this is Ix into Rs. Okay. So just previous one use it, that A plus B plus C is equal to what? So A plus B is equal to C. A is equal to that opposite side. That is, this is minus GMVX plus B is equal to Vx minus Vs upon R naught, and C is equal to Vs upon Rs. Okay, so you can take at that on, and this is what that is. In a one side you are taking, that is minus Gm plus 1 upon R naught minus 1 upon Rs. This is your Vx is equal to what is this? It Vs upon R naught. Is it? And what is the value of Vs? That is Ix into Rs. Just put it here. Vx is equal to Is into Rs. So this is minus Gm plus 1 upon R naught minus 1 upon Rs into Vx is equal to Ix into Rs upon R naught. Yes. So you multiply it, this is minus Gm R naught plus 1 minus R naught into Rs into Vx is equal to Ix into Rs. This is minus Vs. That's why it is problem. This is minus Vs. This is Vs there. This is not this Vs. So this will be not like this. Okay, just redesign it. Okay, there is some problem in this. This is minus Gm Vs. Okay, so Vx upon R naught is equal to 1 upon Rs plus Gm plus 1 upon R naught into Vx. Vs. Is it? And Vx is equal to Ix into Rs. So this is Ix Rs upon R naught is equal to 1 by Rs plus Gm plus 1 upon R naught into Vs. Yeah, Vx. फिर गलत हो गया. Okay. So what is that? Vs is equal to Ix into R naught. That Vx upon R naught is equal to 1 by Rs plus Gm plus 1 upon R naught into Vx is equal to Ix into Rs. Now it is correct. Okay. So what is Vx upon Ix? So Vx upon Ix is equal to multiply with R naught into Rs. So this is R naught plus Gm R naught Rs plus Rs. So this is the resistance. So this is the resistance. If you are looking from this side, what is the impedance? Whenever you have this type of circuit, you can directly write it. What is that resistance? Whenever you have a like this and you have a resistance like this, that is Rs, and you have a here, and you are talking about what is the Z out here. So what is Z out? Simply you think like this is the resistance. Two resistance are in series, so Z out is equal to R naught plus Rs plus the intrinsic gain, that is Gm into R naught into Rs. This is the impedance there. You can check it. R naught plus Rs plus Gm R naught into Rs. So whenever you are looking from the drain side, if you are looking from the drain side, that impedance will increases. If you are looking from the source side, that impedance will be decreases with the effect of intrinsic. Okay. So this is R naught plus Rs plus Gm R naught into Rs. This is the output impedance. Okay. What is the total output impedance? That is Z out is equal to what? That is Z out is equal to Rd parallel of R naught plus Rs plus Gm R naught Rs. This is the impedance there. Okay. So you can figure out that whenever you have a impedance, whenever you are talking about the impedance from the drain side, this is R naught plus Rs plus Gm R naught into Rs. Okay. So please work on it. Okay. And we will work on that circuit designing part. Okay. Firstly, understand about the common source amplifier. Then we go for the common drain and common gate. Till now we completed the common source amplifier as the completing of the source degeneration. Now we are going for common drain and common gate. Tomorrow maybe we will go for common drain and common gate. Okay. So common source amplifier is very, very important. Please revise every concept what is happening. because by this block only we will talk about the current mirror and the differential pair. Okay, so that is the backbone of that, of every analog circuit. Okay, so I hope you will work on it, and we will meet on tomorrow. Thank you so much, dear.